Pairwise consistent measurement set maximization for robust multi-robot map merging. There are various reasons that using multiple agents in an inspection task is useful. In cooperative mapping, we split the work between agents and increase efficiency. In cooperative navigation, one vehicle navigates with respect to a map that is currently being built by another vehicle. In both of these use cases, we need the ability to determine an alignment between robot maps. This is complicated by perceptual aliasing. When multiple locations in an environment look similar to one another, place recognition algorithms can fail, and that can result in outlier loop closures. In simultaneous localization and mapping, outliers can drastically affect the estimated trajectory. While methods do exist to handle these outliers, they require a prior on relative pose or an odometry backbone, which is not existent in the multi-robot case. To handle this, we've developed a method called Pairwise consistency maximization. Given a set of potential loop closures, denoted by the dotted colored lines in this factor graph, we compile them into a set and then try and find a subset of those measurements that are consistent with one another. We do this by looking at pairwise combinations of these measurements and then finding the largest possible subset where every pair of measurements within the subset are consistent. We can solve this efficiently by converting it into a maximum clique problem over a consistency graph where nodes denote measurements and edges denote consistency. We've compared PCM to existing robust SLAM methods on both simulated and real-world data. In the plot shown here, two robot trajectories are shown in blue and green. Red denotes missed outliers, pink denotes disabled inliers, and gray denotes disabled outliers. PCM outperforms residual-based methods like DCS, max mixtures, RRR, and switchable constraints, because these methods require an initial prior or odometry backbone. In addition, PCM outperforms methods like single cluster graph partitioning, or RANSAC, because these methods do not enforce set pairwise consistency. This results in inconsistent graphs. Pairwise consistency maximization guarantees that the set of measurements it selects are pairwise internally consistent. This results in a consistent trajectory. While both PCM and RANSAC have a threshold that needs to be set, as we vary its value, RANSAC's graph is significantly more effective than that of PCM. In addition, PCM's threshold can be set a priori in many cases. Quantitatively, other methods require prior or don't enforce group consistency. This results in the selection of outlier loop closures and high trajectory errors. PCM guarantees pairwise measurement consistency, which results in a high true positive rate, low false positive rate, and low chi-squared error. This in turn results in low trajectory errors.